videotaping my computer too. So if there's an issue, I'll put the videos on YouTube, and you can watch the video of this lecture on YouTube. Okay, so what I want to do today is first talk about what's due this Friday, and then on the 18th. So what I'm showing you right now is what Canvas looks like for you guys. Hopefully you guys can see that. I don't know if I want to make it a bit bigger. The assignment that is due on Friday is a video that shows that you built the electrophorus and the electroscope. Yeah, I apologize, it's blurry. It's my internet's slow. I'm having network issues. So regarding the video, you want to have it, and this can be done in two separate videos. You don't have to upload one video. You can upload two videos, however you want to do it. I don't expect you to be experts in video editing. All right, so if you don't want to combine two videos into one, that's fine. But I need a video showing that you have built the electrophorus. I want to see you in the video with the electrophorus, and I want to see that it works. So, for example, with the electrophorus, what you can do is, once you've built it, you can take a piece of saran wrap, place it on a horizontal surface, and rub the saran wrap with fur to charge up the saran wrap. Then you take the electrophorus, place it on the saran wrap, and with one hand, let's say, touching the water faucet because that's grounded. Your other hand, you can just use your finger and touch the metal part of the electrophorus. Just touch it momentarily. Then you can lift up the electrophorus and hover it over some small pieces of paper that you pre-cut. And you should be able to see that the pieces of paper are moving or are being attracted to the electrophorus. And that's all I need to see. For the electroscope, and then I want to show you the electroscope real quick. Let me switch windows here. This is the website that I linked to in the properties of charge document. And it shows you how to build this electroscope. And again, I want, in the video for the electroscope, show me the electroscope that you built. I want to see you in it, and I want to see that it works. So you can bring a charged object near that ball, for example, and then the video should show that the leaves at the bottom are moving. That's it. So each part is maybe 15 seconds tops. That's all I want to see. So as long as you show me something that's built, it's working, and I see your face in it, you'll get 20 out of 20.
Do you want to see the process of us building it?
No, I don't need that. I mean, that's okay. If you want to show that, that's fine. But I don't need that. Are we okay with that? And the instructions are pretty straightforward on this website. And by the way, you can use, for the electroscope, you can use information from another website to build it. This is just an example. It shows you how to build it. I mean, step by step. It's pretty straightforward. The only words of caution are to make sure that the aluminum foil is not that heavy aluminum foil, but the regular one, because you want the foil to be able to move fairly easily. If you use heavy aluminum foil, it's going to be too heavy for the charge to affect it. Some people have asked, can I use a plastic jar? You can try it. I mean, I think it'll probably work, but plastic tends to get charged, either on the inside or outside, and it might affect your electroscope. So I prefer you use glass jar. If you don't have a glass jar, try to use a plastic one. The lid doesn't have to be plastic. You don't have to have a plastic screw-on lid. You can replace the lid with, let's say, a piece of cardboard. The lid doesn't have to be a screw-on lid. The top has to just be able to cover the lid, so cover the top of the jar. So you can use a piece of cardboard to cover it. Oh, let me see this question. I'm sorry. Yes, all you need to, in the first video, all you need to do is to show that the equipment works, that the equipment you built works. That's it. That's all you're showing in the first video. Then the video that you've created, you will upload. So I'm going to switch to the student view. Give me a second here. And I'm going to scroll down. Property of charge module. And notice in the properties of charge module, there's a video I want you to watch. This is the document for the properties of charge. You can ask questions. And then this is the video for built electrophorus and electroscope. I click here. The window pops up. And then where I'm circling, I click on submit assignment. And I choose file to upload. You can upload more than one file. So if you made 2 videos, just upload your videos where it says choose file. Is that clear? Yes?
Yeah.
Okay, good. Okay, so let me close this window. Let me go back to the modules. Okay, so a couple of things. There's some lab report reminders in here for when you start writing a lab. So make sure that the stuff on week 0 you've read everything. Then on the 18th, you're going to provide me the lab report for the property of the charge lab. It's a video lab report. So let me switch to the lab itself. I closed the file. Hold on, let me open. Let me open the property of charge file. And you all can see the file for the property of charge lab. So, and I've done this in all the labs, and I noticed a mistake. I'll tell you about the mistake in a minute. So I list the equipment you need for the lab, and the stuff we will provide for you, and the stuff you need to provide, and you can just look at the footnotes. One mistake is the transparency sheet. We don't provide the transparency sheet, but you can use the saran wrap instead. The saran wrap will work. Actually, I think the saran wrap probably works better, as long as you can keep it flat. Okay. So everything you need is listed there. Let me scroll down. In part 1, and the instructions are pretty straightforward. You take a balloon, rub it on your head, and put it on the wall. Is it stick to the wall? Yes or no? Why? Okay. Rub the PVC rod with a fur cloth and place it near a narrow stream of water. What do you notice? Does anything happen? Why? In the video, you're going to demonstrate and explain why. So in part 1, there's several things that ask you to demonstrate in your video. You don't have to demonstrate everything that is in the procedure, because a lot of the explanations are essentially the same. So if you can show me 3 out of 4, or I forget how many things there are there, items, that's fine, because I think the part with the salt, you don't have to show, but you can talk about it in the video. Okay. You can talk about what happened when you did the salt part, but you don't have to show that part. Does that make sense? You just have to explain what happens in every case, but you don't have to show what happens in every case. You don't have to do a demonstration, you just got to explain. Are we clear on that? Okay. Part 2 is the PVC rod, the glass, and the electroscope. And really, it's basically has you go through and try to understand how the electroscope works and how you use it. So you kind of have to think, play around with it, do some experimenting, do what's what you're asked to do there, but do some experimenting so you can understand how the electroscope works. And of course, we have a discussion board. You can always ask questions. Once we have finished distributing lab kits, Tyler will probably have office hours too to help you with the labs. And he's probably going to be creating videos to demonstrate experimental procedures. Not for this lab, but the future labs. Okay. So for part 2, what you'll be doing, just a second here. What you'll be doing is going through these steps, observe, and you want to explain. Like I said, you don't have to demonstrate all these steps in the video, but I'd like for you to talk about the things that you observed and explain why something happened. Okay. And part 3 is electrophorus. Now, normally this lab has 5 parts. I got rid of 2 of the parts. Part of it, I didn't want to make it too long. Another reason why is because the equipment you won't have at home. We usually do something with a Van de Graaff generator, and the students have fun with it, but it's hard to do that when we're online. In fact, I like doing demos with the Van de Graaff, and I can't bring it in my room here because I might blow out my computer. Okay, so I am kind of stuck doing less demos. I would have had video demos, but because of the lab kits, we haven't had time to make videos. So electrophorus, actually, the first couple of parts of electrophorus you essentially do in the first video. Okay, but ask interesting questions. For example, if you charge the electrophorus a certain way and then you want to recharge it again, can you, without rubbing the saran wrap with fur again? Can you repeat the process endlessly? That's one of the questions. And so you have to be careful in this part. Sometimes it doesn't work very well, sometimes it does. And it really depends on conditions. If it's moist in the area where you're at, what happens when you charge something, the charge will actually get transferred to the surroundings, into the moisture. You want to be careful. The lab should work at this time of the year because it's dry outside, but you never know. It could be locally, maybe the humidity might be higher in the room or something. Questions or concerns? Are we doing okay?
When is this one due? The second lab?
It's due on the 18th of September, so let me go back. So it'll be due, I'll expand this, sorry. September 18th. So that one's worth 40 points. The one that's due on Friday is 20 points, and that should be an easy 20 points because really all I'm looking for is you showing me yourself in the video and a device, 2 devices that work. If you can do that, you get your full 20 points. Okay. The video lab, I'm trying to see if you can explain things correctly? Do you understand what's going on? That's what I'm going to be asking myself.
So for the video live, for the second one.
I'm sorry?
Yes, I mean for the video live, for the second one.
For the second one, yeah?
Yeah, do you want to explain those things in the video? Or write down those things and turn in the other file?
There's no there's nothing written that you have to turn in. You just, everything that you do is in the video. So you explain everything in the video.
So it's just like explain, speak, and recording the video.
Yeah, you show somebody a portion of the lab and then say why something. Why did the balloon stick to the wall, for example? And you can, if you have a whiteboard, you can write on the whiteboard and explain.
Gotcha, thanks.
Okay.
But all those things are in the video, and we don't need to turn in the other file, but all in the video.
Everything's in the video. You don't have to.
Gotcha,
you don't have to write anything.
Thanks.
I think it actually helps you to better understand the material because you want to say something correct when you do a video, right? As opposed to when you write something down. You have to be a little bit. People tend to be a little bit more careful when they make a video. At least I hope that's what happens. Other questions? Now, I want to show you a video. One of the videos I didn't play in class. Sorry, that didn't work in class. I want to show it to you. It's strange. For some reason, it closed. Not that one. Sorry. Okay, let me just show you this video that I skipped so you can get to see what the field lines look like.
To the ground attachment of a Van de Graaff generator, we connect a large conducting sphere. When we turn the generator on, the generator's sphere becomes strongly positive in charge, and the other becomes strongly negative. We sprinkle bits of fur into the air around the spheres. A very distinct, stable pattern appears. This pattern indicates an electric field. Notice that the field is not quite symmetrical. This is caused by the presence of other conductors, such as people, in the vicinity of the spheres.
So that video shows you basically what you see there are field lines. Okay, what you're seeing are field lines. Okay, and that's what I want to illustrate in that video. Okay. So what I want to do today, if you guys don't have any questions regarding the lab, I want to say a few more things about properties of charge. Let me close one more window. And I want to talk a little bit about the dipole. So before I go on, anybody have a question? Okay. So I want to show you an application of this idea of the properties of charge. And it's the copy machine, also known as the Xerox machine. And I'm hoping you guys can see this figure. This is an example of one. I'm only going to talk about the black and white Xerox machine. So there's a big drum. It's called an electrostatic drum here. And in the drum itself has a coating of a photoconductive material. It's called generally selenium. And it's negatively charged. When you shine light on it, the selenium conducts electricity. When it conducts electricity, the electrons, the negative charge goes into the drum, making the selenium neutral. So here's a document at the top here. You put it on your Xerox machine, and what happens is you shine light on the document. When you shine light on the document, let's say you have a document of a figure, okay, somebody's face, for example. When you shine light on this thing, wherever there is ink that corresponds to the figure, the light will not go through. Wherever there is no ink on the page, the light will go through. So when the light goes through, that's going to hit the selenium. The electrons then are going to go into the drum, leaving the selenium neutral. Wherever there is an image of this person's face, the light will not go through. And so the drum itself then will stay, that section of the drum itself will stay charged negatively. We basically have an image on the drum that's on a sheet of paper. And that image is lined out by the charge that's left on the drum. Then you send in some toner, which is positively charged. The toner then will stick to the selenium coating. And so now you have toner in the shape of the figure. Then you send in the sheet of paper. The sheet of paper is, as it's sent through, is made negatively charged with a higher negative charge than the selenium. And so what that does is causes the toner to be attracted to, because the toner is positively charged, it gets attracted to the paper. The paper then is heated and sent through rollers so that the toner goes into the fibers of the page. And then the paper comes out with your copied image. And so it's using properties of charge to produce an image. It's one of the examples of the application of electrostatics. The inkjet printer uses electrostatics too. All right. So I want to talk about the physics of electric dipoles and electric fields. Remember from our discussion last week that electric dipoles exist when the center of positive charge in a molecule does not coincide with the center of negative charge in the same molecule. Really what you end up having is an asymmetric distribution of positive and negative charge in the material. Like water inherently has an asymmetric charge distribution, and so it inherently has a dipole moment. So when I did a demonstration last week with the 2x4 and the rod, I brought the charge rod near the 2x4, and then what happened within the 2x4, I was able to separate the positive and negative charge. The opposite charge stays closer to the rod, and the charge that was the charge in the molecule that was the same as the one in the rod tries to stay far away from the rod. That produced an attractive force. And we defined the dipole moment as P equals Q times L. Q is the value of each charge. And L is the vector that is directed from the negative to the positive charge. Now, remember we talked about two types of molecules. There's the polar molecule where it has a permanent electric dipole moment, like water. You guys probably all know more molecules than I do that are polar, unless you do that chemistry. And then there's the nonpolar molecule where the centers of positive charge and negative charge coincide, so you get a symmetric charge distribution within the molecule. Of course, you can always polarize a nonpolar molecule by bringing a charged rod or putting the molecule in an electric field. The idea of the electric dipole moment comes up quite a bit in physics. For example, when you're talking about microwave ovens, radiation from atoms, radiation from antenna systems, or when you look at the interaction between neutral atoms. It's actually used a lot in approximations. So a lot of times when you're talking about how electromagnetic waves are distributed in space, you end up having to do an integral. The integral tends to be difficult. And so what physicists generally try to do to make the integral easier is that they expand the integrand, the terms in the integrand, in a power series. When they do that, the first term has a Q times L in it. Or has something of that form. We call that the dipole term. That term is easy to work with when you're doing calculus. The rest of the terms are very complicated. So what we do is if the other terms are small, we ignore the other terms and just focus on that first term in our expansion. We call it a dipole approximation. And that's used when, for example, we talk about the radiation from atoms. Okay. And so it's used in various fields of physics to do calculations. That's why I want to spend some time talking about the electric dipole. It's analogous to something that's done in 215. In 215, you learn about how the mass in the spring oscillates. There's a lot of systems that oscillates very similarly to a mass on the spring, or approximately similar to the mass on the spring. And so that particular problem is called a harmonic oscillator problem. And so you'll see a lot of approximations made where the physics of the harmonic oscillator can be applied, or at least the math behind it. So we do this in physics because it makes the problem easier to handle. The dipole is one, and then the harmonic oscillator is the other one. So what I want to do is I want to consider the electric dipole in several situations. So let me change my, actually let me erase my board real quick, and then I'm going to change the view on the screen so you can see the board. I'm not showing the board right now because I'm erasing it. Give me a second here. Okay, so let me switch views. Okay. All right, so I want to talk about the dipole in an electric field. What are some physical things that we can glean from it? What can we learn? Some of the things I'm going to say are actually in chapter 25, but that's okay. I mean, most of the physics you already know. That's not a big deal. Okay, so let's say we have a dipole in an electric field. And let's assume that the electric field is uniform. It means the same value everywhere in space. Okay? Let me draw an electric field. And let me draw a dipole in the electric field. I want to know the force on that dipole. I need to remember this equation, F equals Q times the electric field. In order for me to be able to understand or look at the sum of the forces acting on the system, I have to draw a free body diagram. Okay, remember, anytime, again, even in this course, you hear the word force, you should think of free body diagram. So the field here and the field here are the same because we said the field is uniform. The field points to the right, but on a negative charge, if I take the negative charge times the electric field, it's going to flip the vector around, and so the force is going to point to the left. On the top object, which is positively charged here, the top object on the right, the force on it is going to be in the same direction as the electric field because of the fact that Q is positive. And since the magnitude of the Q's are the same and the E's are the same, those forces are equal and opposite. So when I sum the forces, if I sum the forces, I'm going to get minus Q times E plus Q times C. I get 0. So when you have an electric dipole and a uniform electric field, the net force on it is 0. But it's not an equilibrium. And I'll give you an example similar to this. Suppose I have a square plate pinned in the center. I apply a force to the left on the bottom left-hand corner, and I apply a force on the right, to the right, in the upper right-hand corner. The sum of those two forces are 0, but that object is not in equilibrium. It's going to want to spin. Both of those forces produce a torque. So in the case of the dipole, we have the same situation. Compare the free body diagrams. You're going to have a torque on that dipole. In fact, what the dipole is going to want to do is align itself in the direction of the field. So what this will do is, it'll speed up, hit the horizontal, but because it has speed, it'll overshoot it, go to a maximum value, and come back. And so this dipole will really oscillate back and forth like that. That's what it will do. That's because there's a torque on it. And so the question is, can we calculate the torque? Well, of course we can, because we know what the definition of torque is. Torque is R cross F. And so what I'm going to do, let me erase all of the free body diagram. I want to find the torque. Let's say I do the torque about the center of this system. These two objects are somehow linked together. I can think of it mechanically that they're linked together by a rod that has no mass. Okay, if you want to think of it, how they would be linked together. So, and then I want to find the torque about the center of mass. I want to define a vector. My R goes with L over 2. This R is minus L over 2. The force is Q times V. So my R, I'm going to put in my equation is L over 2. My F is Q times V. And so for this object, the torque is going to be L over 2 cross QE plus negative L over 2 cross negative QE. The negatives cancel, leaving you a positive. When you sum them together, you get L cross QE. The Q is a constant, I can move it anywhere. So I can write it like this. But we define Q times L as the dipole moment. That's it. So the torque on a dipole in a uniform field is given by this expression. If the field is non-uniform, it's more complicated. I'm not going to do that problem. Now, the electric field, the static electric field here is a conservative field, and we'll learn about this later, which means you can define a potential energy from it. When this object rotates in the field, the torque is actually doing work on the dipole. And you know, for conservative fields, the work done is minus the change in potential energy. And so I'm going to derive an expression for the energy stored in the dipole that's in a uniform field. I need to pull out an equation that you might have seen in the previous course. It's in the chapter on rotational dynamics. If you did have 205 here, then it would be chapter 10 of the textbook. And the equation says that the work done by a torque is equal to the magnitude of the torque times d theta, the small angle of rotation. And I hope you remember that the magnitude of the torque can be written as the magnitude of P, in this particular case, times the magnitude of E, times the sine of theta, the angle between these two vectors. If I wanted to do in general, then this would be an RWF. This is Q times, no, just P, that's it. So I'm going to write in here P times Z, these are magnitudes, times sine of theta, d theta. Now here's a problem. This is the angle theta. Theta actually decreases. Usually when you do problems like this, theta is increasing, but theta is decreasing. So our d theta is actually getting smaller. That means I have to stick a minus sign in front of this guy, because this d theta is really less than 0. Now, you'll learn that dW is minus du for a conservative force. You learned that in physics 205 previous course. So if these two are opposites of each other, then du is a negative of this. And if I integrate this from some initial angle to some final angle, that's going to give me the change in potential energy. So I want to integrate this expression from an initial angle to a final angle. The integral of sine of theta is minus the cosine of theta. And so this results in the following. You get the magnitude of, minus the magnitude of P times the magnitude of the E times, in parentheses, cosine of theta final minus cosine of theta initial. Now, this expression, U is always defined to within a constant. Potential energy is always defined to within a constant. So, if I define U at theta equals 90 to be 0, and I let U initial occurs at theta equals 90, right? Let U initial occur at theta equals 90, then U initial equals 0, and U ends up being minus the magnitude of P, the magnitude of E, cosine of theta. This is the dot product. And so the energy stored then could be written as a dot product between the dipole moment and the electric field vector. Again, this is for uniform fields. So a couple of questions to ask. What is the torque on electric dipoles that are induced in a nonpolar material when placed in an external field? I got to think about this carefully. When you have a nonpolar material and you put it in an electric field, the dipole will automatically be formed in the direction of the electric field. That means it ain't going to want to rotate because it's oriented in the direction it wants to be oriented in. So there won't be any torque in this case. There will be no torque on an electric dipole that is induced in a nonpolar material when it's placed in an external field. Okay, Damien, I'll repeat it. So, you have no dipole, you introduce a field. The plus and minus charge will be separated along the direction of the field vector, isn't that true? That means it's not going to rotate. It's already where it wants to be. Okay. Now the next question is a little bit harder, so I have to do a little bit more work. What is the net force on an electric dipole that's placed in a non-uniform electric field? So that's going to require me to do some work. So, look on the board. The answer is not 0. We do get a nice expression. I'm going to do a special case because it makes the math and the calculus a lot easier. But one can generalize this for any arbitrary orientation. In my example, let's say we have an electric field that points to the left, but its value changes as you go to the left. But the change, it's a well-behaved function, not some screwy function. With this continuities or anything. So I'm assuming a well-behaved electric field. So let's assume that varies with x. And it's in the x direction. Okay. And let's put a dipole. And again, I want to make the math easy. I'm going to make the dipole oriented already in the x direction. Of course, you know I've exaggerated this distance, right? The magnitude of the distance between these two is L. So the field here is different from the field here. If I define my coordinate system so that the origin is here, this location is x. And let me call it, instead of calling it L, I'm going to call it delta x. This location is x plus delta x. So the field on the charge at the left we'll call E of x. The field on the charge at the right will be E of x plus delta x. Again, I can draw a free body diagram and say, oh, well, the force on the object on the left points to the left, and its value is Q times this thing. The force on this object, so I'm going to call this F1, and this F2. This one points to the right. Its value is Q times whatever the electric field is at this point. So the sum of the forces is Q times, let me write it this way. Give me F2 minus F1. Which can be written as Q at E of x plus delta x, Q times this, minus Q at E of x. Just for fun, let me multiply numerator and denominator by delta x. There's other ways to approach this at this point on, but let's do it this way. So let me write it that way. Multiply the numerator and denominator by delta x. And of course, Q times delta x is basically P. So I'm going to call this P. Let me erase this and call it P. The magnitude of the dipole moment times this thing. Now in reality, L is tiny. Yes, Damien. That's what I'm trying to do. I'm going to let delta x go to 0. What is that when I let delta x go to 0? This is a derivative. You can write it as a
Can't see
derivative.
that far down.
Is it too far down?
Yeah.
Okay, let me.
Can you also explain how you got the dipole for that equation, that P?
I'm sorry. Say that again.
The P and the delta X.
This one.
Where does that come? Well, the second one, the second equation, how it's divided by delta X.
I multiply numerator and denominator by delta x. Basically, I multiply by 1. Right? It's legal.
Where's it in the numerator? I mean.
Remember, P is Q delta x. That's by definition, right?
Oh, okay.
Right? Because I wrote it before, and then I said, that's just P, so I erased it.
Gotcha.
And so it can be written as derivative. Now, if this was oriented at an angle, life would be more complicated. Okay. And you get a much more complicated expression. If I have time next week, I might talk about that. But it's not a nice. It's a compact expression, but it looks very foreign when you do that. When you do a general case where the electric field has x, y, and z components, and the dipole moment has x, y, and z components, you have a complicated expression. It's compact, but it looks like foreign. It looks weird. It looks like something you've never seen before. I shouldn't say weird, it just looks different. Okay. I want to say one more thing. Regarding Coulomb's law, and this is just of interest. Many years ago, around 1910, Rutherford conducted an experiment to study the structure of the atom. And his results, well, one important result was that he was able to show that the atom consists of a center of positive charge, the nucleus. They also verified he also verified Coulomb's law in the process. So let me briefly talk about this. So Rutherford did an experiment where he scattered X-rays off of gold foil. Basically, the X-rays, not the X-rays, the alpha rays. The alpha rays are helium atoms with the electrons removed. The alpha rays are scattered off the atoms in the gold foil. And again, he was trying to study the structure of the atom when he did this experiment. At the time, the model for the atom was that you have electrons embedded in a fluid of positive charge. And this whole thing was neutral, called the plum pudding model. And Rutherford wanted to test it. And so he sent alpha rays, which are basically helium atoms, towards gold foil so that they scatter off the atoms. And he got an unexpected result that these particles got scattered backwards. And he was trying to find an explanation. And so he devised a model and did a calculation based on the model. And in the model, he assumed that the atom consisted of a center of positive charge. The protons are all in the center of the atom and the electrons far off somewhere. And he assumed Coulomb's law. So when he did the calculation, to calculate what would happen, what would the distribution of alpha rays be when he used his model agreed with his results. And so at that time, then it was established that the atom consisted of a center of positive charge. But in the process, since he used Coulomb's law, he was able to verify Coulomb's law. So he indirectly verified it. Okay. By the way, just FYI, he won the Nobel Prize, but I think 10 of his graduate students also won Nobel Prizes. They had a really nice lab setup. In fact, I think if you see, I'm going to scroll back. A couple of people who did the measurements in this project were Geiger and Marsden. You know who Geiger is, the person who developed the Geiger counter. Geiger and Marsden developed the Geiger counter. They won Nobel Prizes too. Any questions? Concerns? Let's see, what time is it? We got 10 minutes. No questions. You guys doing okay at the homework? Homework going smoothly? No questions? Okay, that's good. Homework's going smoothly. Let me know if there's any issues with the website. I think we've got that under control. And my screw up is under control now. Now, one thing I forgot to tell the class, I'll tell you guys, is a bunch of you are on Discord, and it's really cool to see you guys helping each other doing the homework. Yeah, I understand. It's hard to get accustomed to being online. I know it's hard to teach online. It's hard to teach without seeing people's faces and seeing the look in their eyes when they describe something abstract. But yeah, a lot of you folks are using Discord, and every once in a while I pop on to see what's going on if people need help. That's good. I mean, this is what we need to do to help us learn the material, because we're kind of isolated right now. We need to do whatever we can to help each other out. So I go on there, and there was a question on there the other day, and I answered it for students. Just make use of things like Discord discussion boards so we can help each other. One more question. You want to make sure that we don't have to do... No, just the 9th edition homework 1. Remember that the other one used the wrong edition. I'm going to make all those assignments, the rest of the assignments that start with Physics 210, I'm going to make them unavailable to most students. There might be a student who paid for the other edition. I'll make it available the homework available to that student, but for everybody else, I'm going to make it unavailable. So even if you click on it, nothing will happen. Okay. Yeah, I'm sorry. It looks like a mess in the grade book. That was just a mistake I made. I saw this thing update when I created the course, and without thinking, I pressed the button. I think that's what happened. In 2 weeks, I still haven't got a response from WebAssign. So anyway, at least this worked out. Any other questions? Okay, I'm a little bit behind in the lecture, so what I might do next Wednesday, I'll probably use some lab time to lecture. So next Wednesday, again, we're still going to be working on this first lab, so if you have questions on this first lab, please don't hesitate to ask, okay? All right, so I guess we're done. So we will see you maybe in 210. I'm going to end there now.